Hello everyone. In this lecture we will discuss inductance. To understand this, suppose we have two wire loop. Suppose this is a loop 2 and here we have a second loop. Suppose this is loop 1. And suppose here steady current I1 flow through this loop. So when steady current I1 flow through this loop, then it produce magnetic field. Suppose this is a B1. Then some lines of magnetic field also passes through loop 2. That is, here also we have B1. So here conceptually, when steady current I1 flow through loop 1, then it produce magnetic field B1, and some lines of magnetic field are also pass through loop 2. Now here suppose phi 2 be the flux of B1 through loop 2. So when phi 2 be the flux of B1 through loop 2, then phi 2 is equal to B1 into dA2. So here B1 is the magnetic field. So in term of potential, we can write curl of vector potential, and here we have dA2, or we can write A1 into dI2. So here we apply Stokes theorem to convert surface integral into a line integral. But the vector potential is equal to mu naught I1 over 4 pi and dI1 over R. So when we substitute the value of A1 in above equation, then we can write phi 2 equal to mu naught I1 over 4 pi, and here we can write dI1 over R and into dI2, or we can write mu naught I1 over 4 pi and double integral of dI1 into dI2 over R, or we can write this phi 2 equals to M21 I1. So here M21 is equal to mu naught over 4 pi and double integral of di1 into di2 over r. So here M21 is equal to mu naught over 4 pi and here di1 di2 over r. So this is Newman formula. This is the Newman formula. So here it involves a double line integral, one around loop 1 and second around loop 2, and this M21 is the mutual inductance of two loops. Then further this M21 is purely a physical geometrical quantity. It is M21 is purely geometrical quantity. Geometrical quantity mean it depends upon size, shape and relative position of two loops. Relative position of two loops. Okay. So here M21 is the geometrical quantity, that is size, shape and relative position of two loops. Further, if we change the roles of loop 1 and loop 2, then we can write M21 equal to M12, or we can write this is equals to M. Okay. Further, now suppose we vary the current in loop 1, then definitely there is a change in flux in the loop 2, and as per Faraday law, induced EMF is equals to rate of change of flux with respect to time. And further, so phi 2 is equals to M2 I1 M21 I1, so we can write this is equals to minus M di1 over dt. Okay, so here in this case the induced EMF is equal to minus M di1 over dt. So this is the mutual inductance. Further, so here if we change the current in the loop, then it not only induce the flux in the nearby loop, but it also induced an EMF in the source loop itself. I will repeat the same. So when we change the current in this loop, then it will not induce EMF in any nearby loop, but it also induced EMF in the source loop itself. So here when it induce the EMF in the source loop, then in this case phi, that is flux, is directly proportional to change in current, or we can write this is equals to Li. Okay, then so here it means flux is equals to Li. So L is the proportionality constant and known as self-inductance. So here L is the self-inductance. So again this L is a geometrical quantity. That is here in this case it depends upon the size and shape of source loop. Okay, so here again if we change the current, then induced EMF is equal to minus L di over dt. Then here this inductance, either we have a mutual inductance or we have a self inductance. They intrinsically these are the positive quantities, but here this negative sign shows that this induced EMF oppose the change in current. So this is due to this reason this is known as back EMF. This is known as a back EMF. I will repeat the same. So as per Lenz's law, here negative sign indicates that this induced EMF oppose the change in current, and due to this reason this EMF is known as back EMF. Further, finally, if the inductance is very high, if the self inductance that is L is very large, then it is very difficult to change the current. Okay, thank you.